Hello, my name is Andrew Harrison. I'm a professor here at the University of Cincinnati, and today I'm going to be presenting about data integration and how it forms the foundation for business analytics. So we're going to be going through sort of a general overview of the three different types of data models that are used in polyglot data systems and form the backbone of analytical systems in organizations. And after we talk about the various data models, we're going to talk about how we integrate data from those three into a single system, which is called a mediated schema, that's then used as the basis for most of our reporting and analytics. So to do that, we want to start with a business problem. And so we're going to work through an example so that we have sort of a solid background on how this is applied in a organizational context. And so that you can draw some inferences to your own work as well. So the business problem we're going to start with today is the example we'll be working from is in a financial processing institution. So when a transaction is created through a website in a financial organization's website. So if someone tries to make a bank payment on the bank website or something like that. And so the systems that we use are going to be integrated to take that transactional information from the bank, and it's going to reference it against previous transactional history. And so to do that effectively, we really want to start with a business case problem, and we want our solution or our polyglot system that we're going to be developing to be based around what the business process needs. So really to do that, you need to start all of these technical solutions with business acumen. So it needs to be driven from business sense for a business purpose so that you can apply it to either make money or spend less money in your organization. So in this case, what we want to do, or the question we're trying to ask ourselves, is how do we rate these transactions that are occurring on the website? How do we determine which ones are legitimate, which ones are fraudulent? So how do we rate them so that we can automate some of the screening of these processes and treat these transactions differently depending on context? And so the core to this is what types of information are going to be useful for helping us make a good evaluation about whether these transactions are legitimate or not. And so we would need to go and we'd start to ask some of the fraud experts within the organization, what are the key factors that we would want to look at and evaluate to determine whether a transaction is legitimate or not. And so they usually would be able to come up with a list of the criteria that we would want to use. And so that's where we basically start our problem. Is we evaluate the grain that we're going to be looking at, and we try to figure out, and the grain means from a mathematical level, it's what each tuple represents within a relation, or another way of saying it is it's what each line or row in a table represents. So we want to figure out exactly what each row is going to represent in our table. In this case, it's fairly easy. It's going to be a transaction. And we want our transaction, which is represented by one row, to have some rating that accompanies it and tells us whether the transaction is legitimate or not. So to do that, though, we need to evaluate and combine a number of different data sources so that we can store things like customer data with the web portal data, with existing data from, say, either large scale, like nationwide resources like the IRS or some of our competitor data even. And we want to be able to combine that and conglomerate it all together into a single system where we can then use various fields from multiple systems, combine them all in a way that's useful, and then we can analyze our transactions in accordance to that. So we need to consider, after we determine from the experts what are the fields that we need to answer our question, we need to figure out where those fields exist. What systems can we pull that information from so that we can ultimately merge it together. And so in this case, we would be developing a two-step process whereby first we would be taking the information from existing data sources, and we would create a one mediated schema. And this would be a physically mediated schema, meaning that it would basically be stored like a table. So we would take all this data together, run like a SQL query on it to combine it all together, and it would become a SQL table. And then we would take the analytics from that table, which in this case we would probably run some type of logistic regression model. In this example, we're going to use a probit model, which is basically just a varied probability function for regression analysis. that'll give us a outcome that's either fraudulent or not fraudulent. So it's a probability-based model. And then we would apply that probability-based model that we used on the first physically mediated schema that contains all previous transaction history, and then we'd apply it in real time to what's called a virtually mediated schema. And the virtually mediated schema would be like real-time processing of the information as it's actually being accrued by the website and the organization. And so really we have two different mediated schemas going on here. The back-end schema that's going to be developing a model that we can apply from existent data, and then we're going to be applying that model from the extant data into the real-time data as we accrue it. And so we would revisit what the customer said, and we would try to figure out, what are these different fields that we're going to need to analyze the data. And so in this example, we identified these 8 fields. So transaction amount, whether the transaction is international or not, or if it's from a high-risk area, which are related to previous transaction histories, along with factors that are related to the customer themselves, which may be some external credit score rating, the general information about how often or how frequently the customers interacted with the bank this way before, and then some other factors like their level of wealth, whether it matches the type of deposit or withdrawal that they're trying to make, and then some behavioral factors as well, which would be like how often they move the cursor, how many times they change the amount on the form on the website. And those factors will all be combined together so that we're using some of these behavioral issues along with the historical data about the customer that we can glean either from our own data or from third-party vendors, along with actual transaction factors about previous transactions and the likelihood of fraud associated with those transactions as well. We're going to combine this all together to try to make a system where we can actually make useful predictions about whether or not a transaction is legitimate or not. And so to do that, what we're going to do is combine data from different data models. And so each of these data models, the relational model, the dimensional model, and the key value model together make up what's called a polyglot data system. And a polyglot data system simply means that it's one that uses multiple data models together. And the best analogy for this is it's very similar to, say, a spoon, a knife, and a fork for eating. Each one has a purpose, and they're used well when you use them together. And that you can apply them to a number of different situations, but they're going to have benefits or drawbacks depending on what you need specifically for that situation. So in the same way that, say, eating soup with a knife is not very effective, using, say, a key value data model to process transactional data would also be rife with all sorts of errors or miscues. So each one is better or worse at different things. And the reason that they're better and worse at different things isn't purely by chance. It's because there's actual math associated with each of these data models, and they have different mathematical assumptions and different structures depending on what the math is trying to do. So a relational model tends to be very, very good at data integrity. It prioritizes that over all other things. So you can be confident in a relational model, your data would be accurate, consistent, reliable. On the other hand, dimensional model sacrifices some data integrity to create a system that's more streamlined and flexible for reporting. So you see that you'll be able to roll things up or down depending on the level that you want to look at things. So they tend to be the basis of reporting systems where you need features like that, and you need to be able to look at reports at either a daily level, a weekly level, an hourly level, a quarterly level, a year, and you can roll up and down between those seamlessly. Then in a key value model, we basically trim out all these associations that we use in other forms of model. But what that allows us to do when we trim out those different associations is we can split up big problems and chunk them up and process them in parallel. So they tend to be really fast in terms of being a workhorse, but the cost of losing those associations between different pieces of data mean that the key value systems tend to struggle with data integrity. And so because each of these is good at some things and bad at other things, and in a modern system, what we tend to do is actually combine them in different ways so that we can take advantages of the relational aspects when we're doing transactional type data. And we can take advantage of the dimensional aspects when we're doing reporting based systems. And we can take advantage of key value structures when we have a lot of processing. And so each one is slightly different, is beneficial in different circumstances. So in a relational model, there's a lot of interrelationships between pieces of data. And so this is basically based on like 400-year-old matrix algebra. So based on the work of like Rene Descartes. And the way that the pieces are related together, it means that the basis of the relational model is that there's relationships between all the attributes or all the columns within a database, so that these are hidden and latent in some cases, and you can't necessarily see them. But there's what are called functional dependencies that exist between attributes. And so every attribute in every relation or every table is related to every other attribute in a table. So that means that when you enter a zip code in one area, it's actually related to, say, the customer login in an entirely different table. And so all the pieces are somehow related to everything else. And from those relationships and these strong latent bonds in between the pieces of data, we're able to derive data integrity. That is, we're able to enforce our database in a way that we can ensure that a database has characteristics that make the data accurate, reliable, and consistent. So we can be sure that the data is structured in the correct way. In contrast, in a data warehousing type environment, we use a different model called the dimensional model. And that's because all those interassociations between the pieces of data that we talked about in the previous model aren't very useful in a reporting context. They actually slow things down because every time we try to draw data out of it to try to make some type of report, all those interrelationships need to be accounted for, and it bogs down the computer. It takes more time and more energy and more resources to be able to process the data. And so we switch to using a different type of data model that's related to relational, but it's slightly different. And what this means is in a dimensional model, you have a highly normalized centralized table, which is called a fact table. So in this case, in the fact tables usually adhere to some type of report. So in this case, we're seeing a fact table for a customer transaction summary report. And so then it would be linked to a series of other non-normalized tables, which are called dimensions. And so these dimensions that can be used over and over to conform across multiple fact tables in a data warehouse environment allow us basically to reuse different dimensions in different ways to create different views of data. And it creates a really flexible reporting system so that you can aggregate things together, say by customer or by account in this example, or you can roll things together and look at them at either like a customer level or a monthly level, or you can change the time dimensions. And it creates a lot of different options for you in terms of reporting. And it does that in a very, very fast way. So you can run your reports very quickly and get that information into your hands so that you can make good business decisions. And so whereas a relational model would have been really well suited for transactional systems. So like when someone pays, that's the type of data model that you'd send the data into so it could be validated. This model is more skewed towards being used for reporting circumstances. So most reporting systems will use a dimensional model. And then finally, we have a key value model. And this is sort of the third leg of the data modeling stool. So, and this is the model that fits either like NoSQL data or big data as well. And so like a Hadoop or HDFS system uses this structure, and it basically splits all those associations out. So data is very, very loosely associated with other pieces of data. There's not strong associations between pieces of data anymore. And so it's possible to sort of make workarounds and link pieces together. And that's what you'll see certain types of engines like Hive in a HDFS environment does that. And it creates roughly some similarities between, say, a dimensional or a relational database system, but it doesn't have the same key features. And because it lacks some of those associations, an HDFS model would typically struggle with data integrity. But what it gets in contrast to that is it's going to be able to process and chunk up these problems in a way that you can process in parallel. And because there's loose associations between pieces of data, it allows us to separate pieces out and make what used to be like one really big processing problem into a lot of little ones. And so we can process in parallel on a cluster and make things go really fast. And so this tends to be the way that we approach really big sets of data. So data that comes really fast, or data that's from a really high volume source that we don't have another way to process. It's too much data for us to use in a relational or dimensional format. So this would be things like the US Census Bureau data. It's open source, but it's also, there's so much data there, it's really hard to get at. Or patent data, credit bureau data a lot of times, and in more modern organizations, sensor data as well. In the case that we're going to be investigating, there's a lot of analytics that we do for how people use websites now. So it's not necessarily what they're entering into the form on the website, but say how their cursor's moving on the website, how long they loiter on certain screens on the website. So to give you an example, if you're filling out a mortgage application, it's not necessarily the value that you put in your income that matters. There's actually a higher correlation between whether your mortgage statement will default or not based on how long you linger and how many times you replace the value in your earnings. And so it's this metadata that we accrue through your actual behavior that we can evaluate as well. And so in a modern system, you don't actually use any one of these individual structures. You actually use all of them together, and that's the idea behind a polyglot system. So polyglot systems are sort of the basis of data analytics now, because most data analytics models are going to be stronger the more elements you can add, or the more useful elements you can add. So we kind of go out fishing and we try to find different attributes or characteristics of customers or transactions or whatever that are going to help facilitate better analysis. So we're going to be able to add to our analytical models and tweak those models to make them slightly better. And so that's what data integration is about. Is when done successfully, you can take data from any of these different data sources and combine them together, because like I was saying earlier, each of those models is loosely based on the same mathematical principles. They're all based on matrices, and they structure them in a different way. So that in a relational model, you may have like set theory relational algebra, whereas in a big data context, using a key value data model, you're basically using associative arrays and you're moving around things that are paired. But you can use the math behind analytics to combine them together, because at the heart, all of them are basically just a bunch of matrices. They're a bunch of two-dimensional matrices that are manipulated in different ways and use different mathematical associations. And using those principles, we can integrate them together. So to help us out in this, there's actually a formalized data integration process that we can use, where we can transform data from all of these different data models. It's agnostic to the structure of the data, and we can combine it all together into what's called this mediated schema. And a mediated schema is a really crucial part of an analytic system. It's basically a mediated schema. You can think of it as basically a table or a view, or alternately the result of a query. Those are all basically sort of the same things in terms of a mediated schema. But what it means is we're combining data together from different data sources that are structured different ways, and then we're combining them into this mediated schema that will be sort of a structureless data set. Or I guess rather than structureless, you could say that it's a very focused, the structure of the data set is determined by the business problem and is customized to it. And then we use that customized mediated schema to then inform all of the analysis we're going to do. So we're able to build off and draw data from that mediated schema so that we can apply it to make decisions. And so we're drawing data from transactional systems, which would be like your credit systems, or when someone, say, fills out or buys a purchase at your cash machine or something. And we can take that data that's structured relationally, that prioritize data integrity so that the transactions were correct. Then we can combine that with, say, data from either your reporting systems, from like your marketing or financial systems, and or in some cases, even your competitors or your upstream or downstream supply chain partners as well. And then we can combine that with data that we get from the web as well. So things that we pull from places like the Census Bureau or some government data source, or data that comes from our own data sensors. And we can combine that all together into a single schema where we've customized the grain or the setting of that schema to actually make decisions that are useful in a context, or that will improve our data models. All right, so now for the formalized integration process, what we start with, it really has 3 steps. So schema alignment, record linkage, and data fusion. And while it seems sort of complicated and they're split into sub-steps, it's really not nearly as complicated as it looks. And that's that schema alignment deals with the columns in your database. So the first thing that you do is basically determine the attributes or the columns, and you align them in a way that's going to be useful. So you're accruing all the different columns from all of the data sources that you need them, and you're combining them together using schema alignment. Then the next part is record linkage, which does the same thing, but now you're doing it for the rows. And the idea is you're looking for rows where 2 rows mean the same thing, where there's some sort of duplication in them. And so usually that would either mean where 2 rows refer to the same transaction, or 2 rows refer to the same customer or something. And so what that's about is basically matching the rows. And then finally, data fusion tells you what happens when you do match 2 rows together. You come up with a formalized process to combine those rows so that the grain of your resultant schema, or what one tuple or what one row represents, is consistent with the business question you started with. And so basically the process all starts with a business question. Then you actually work backwards to the data to figure out which pieces of data that you need. That's it, and that seems counterintuitive a lot of times, but that's actually the best way to do this. Is you're creating a customized mediated schema to answer all your business questions, and then you work backwards to link it to the data sources in a way that's useful. All right, so that this is the basic outline of what's going to happen, and now we're going to go through an example and actually talk about how that works. So in the context of evaluating a credit card or a transaction on an online system, what we're going to do is look at a number of different data sources. So we're going to look at things like the previous transactional data that we have from the same customers and from other customers that we can use to determine, like, if the transaction comes from an area that's concerning. So like this is an area that's rife with fraud. We don't want to process that transaction the same way. Or if it's a customer who we've had previous problems with, we probably would treat them differently. And so we'll look at this previous data that we have, and it'll typically be stored in our own transactional systems, or in some cases other transactional systems, but it would be formatted in a relational way. And then we're going to combine that with a bunch of outsourced vendor data that usually we purchase through like third-party vendors. So this would be the most common ones, would be things like people's credit scores. So we're going to take their credit score data and we're going to evaluate that as well. And then finally, we're going to combine that with either data we get from websites, like our own website where the transactions are being processed, or alternately, we'll combine it with data that we get from some open source third-party vendor as well, which a lot of times is going to be government data about, say, risk. And in this case, I think we're going to be using some information that comes from the Census Bureau data that gives you sort of an estimate of wealth as well. And so you combine those all together. And the first step of schema alignment is basically you're going to be using these attributes to make a map. So you're coming up with the fields that you need, which were identified from our business question by our business experts that say that we need these 8 fields. And then we work our way backwards and say, okay, where do we get these fields from? Where do we find the transaction amount? Where do we find whether this transaction occurred in a high-risk area? Where do we find the customer's credit score? How do we know how many transactions a customer's had per month, and so on? We actually trace this. Now we work our way backwards into the data systems. And to do that, we formalize this in a document known as a schema map. And a schema map basically means we're going to list down the left-hand side all of the different fields that we need, or that the business process expert says that we need to be able to answer this question. And for those of you that are familiar with analytics now, you would know that these are basically going to form our exogenous variables. So these are going to be the independent variables that we use to form our model. So you list the independent variables down the left-hand side, and then along the top, you list all the different data sources that you have available to you, and you can list what the fields are and where you're going to get the fields. So in this case, say you'd get the customer score from the customer schema in the score attribute within one of your vendor's data warehouses. And in this case, you'd be taking the 5-digit zip code from a web portal to determine whether a transaction is in a high-risk area. And so you can see that basically you have multiple data sources listed across the top, the fields themselves listed across the left-hand side. And then at the bottom, you'll see a couple rows that are highlighted in a different color. And the reason that we use those is that these rows don't actually appear on the report. And they're not going to be important from a customer's perspective necessarily, but rather how we use them is they're useful in the data integration process. They're going to act as foreign keys, ways to join different pieces of data together. And so what these represent is we look for a way that each system is somehow related to some other system. So in this case, you can see that the vendor data, or the data from a vendor warehouse, is going to be able to be linked to the transactional data via some customer ID. So it'll be what's referred to as the customer ID in the transactional database, whereas it'll be the customer login in the vendor data warehouse. Similarly, the zip code will be able to link the open source data, which in this case was from the US Census Bureau, to the transactional database data. So we're going to be linking the zip code from the transaction table to the zip code field in the open source data. And so in this way, you can show how all the various where all the various parts come from. So you get to see sort of the genesis of all of them, but at the same time, you're able to see how they're going to be combined as well. So this is really useful because it's basically pairing up all of the different columns in your database. And so now how to actually implement this is that you need to create SQL code to be able to write this. And the SQL code, while it can look complex, is actually really simple in terms of the way that the schemas will be designed as a result. All right, to start with, you'll see there's a slight difference between a physically versus a virtually mediated schema. So depending on if you're looking at historic data that already works and it's not time sensitive or not real-time based, you could use a physically mediated schema, which basically will create a table. Whereas if it is real-time data, you're going to use a virtually mediated schema. But all of the SQL statements will basically have the grain determined early. So you'll see that all of the top part of any query will basically represent a single transactional line. So remember, that was the grain of a query, or what one row represented. And then the subsequent information will all be left joined onto it, either through a true left join or left inner join. And the reason is that a left join query mathematically keeps the grain of the query the exact same. So one row will still represent one transaction, and you can left join anything to that transaction, and it'll still, as long as it's a left join, one row will still always represent a transaction when you're done. And so the idea is you can create a large scale query that will adhere to the exact same grain for the mediated schema. And that's a really important criteria, because you'll be able to make sure that the result of your query actually means what it was intended to, or answers the business question you intended to at the end. All right, so that basically is how we determine the columns, and we combine them all together in this mediated schema. So at this point now we'll have data. And the only thing that could go wrong with our data is that you could have multiple rows in this case that mean the same thing, or that have some overlap between them. So like the same transaction could occur twice in some cases. Particularly if you're integrating data from multiple systems. You could have two customers, and in this case, you'd have, say, Andrew Harrison occur multiple times because it's a really common name. And so how do you know which rows are one Andrew Harrison versus which rows are a different Andrew Harrison? So in this case, usually you're going to apply some probabilistic matching schema. Most of the time, it's going to be some probability-based algorithm associated with like cluster analysis. There's basically a whole branch of mathematical science and analysis devoted towards clustering like this. But it's hard if you want to use just a really basic algorithm. There's usually some type of deterministic matching way as well, which would be like date of birth and first name or last name, or social security number or something like that. But basically what you're doing is differentiating the rows now. And so then once you know which parts should be grouped together, so in this case, if you're using a probabilistic matching schema and you come up with some rating where, say, like 80% or more have to of the row have to match, and if they do, then you would say that those two rows represent the same customer in this case. So then after record linkage, you move on to data fusion, which basically says, so now you take those multiple rows. So in the top case, there were like 4 rows that would be combined into the first row in this table. And then there's 2 more rows that would be combined into the second row. And so you're basically saying, you know, like what criteria will I use to determine which field should be prioritized or which field should be overwritten when we have what seems like duplicate rows within our data. So usually the criteria that's the most common for this is going to be like the most recent. So the data that's been updated the most recently will probably be prioritized over any of the data that is more historic. Though there are some other times you would do it if you have more faith in one data source or another. But these last 2 steps, record linking and data fusion, are less about cognitively determining the sources of data and which pieces of data you need, and are more about, like, once you've done that and accumulated data, how do you clean the data up? How do you get rid of any extra rows that are unnecessary so that you can get down to the gritty part of what actually is useful for your data? All right, and so this leads us to how this all ties together at the end. So how one of these polyglot systems actually functions and how it fits together. And so remember in this case, I was saying we're going to use a probit model. So again, that's just it stands for probability unit, and it's a regression-based model where you basically have a dichotomous outcome. So it's either, in this case, it's either fraud or not fraud. And so you're creating some type of rating on the probability that a transaction is either fraudulent or not fraudulent. And the way it works is that you basically fit this probability curve to existing transactions that you already know whether they were fraudulent or not. So the first part of this step, again, is you would create some physical schema from existing data. You'd go back and you'd look at those 8 criterion that the business user had said. The 8 variables that the business expert says are important and can be used to determine whether fraud occurs. So you move back, you find the sources of those data, you link to those various sources of data, and you write your create table statement to create this physically mediated schema that basically draws in all the data from those various sources, both internal to your organization and the data that you got from, say, a vendor or a customer or even sensor data. You combine all of that data together into a table, and then you can run your analytical probit model from it. And the outcome of that would be this probit score that you get. So you would create some type of model. So now the next step is actually applying that model in real time. That's when we get to the second step here, is we take the probit model that's based on existing data from a physically mediated schema. Now we're going to apply it to transactions as they churn into the organization. And so what we do is each transaction comes in, we're going to link to the various data sources, but this time using a virtual schema. And so this is where you see the difference between the 2 types of schemas. As in a physical schema, you're basically creating a table, whereas in a virtual schema, you're creating a SQL query. And it's a more elaborate query, but the query actually updates as the source data updates as well. So as the sources of the data change, that in a virtually mediated schema, the outcome will change in real time with it. So as fast as the computer can process it, the outcome is going to change as well. And so what happens is you start to feed this data into the virtual schema in basically real time. And it's running the same probit model that you had developed from the physical schema and applying it in real time as the transactions come in from those various sources. And the benefit of using a virtual schema that's built this way is when you have it linked to all these different types of sources in a polyglot data system, is the virtual schema is really robust to variations in the time that it takes for different reporting. So if some of your reports or some of the systems say feed you data every 3/100ths of a millisecond, whereas other ones will only change daily, you can actually still integrate them into the exact same query at the same time, and they can still apply the data even though one of them varies every day and one of them varies hundreds of times a second. So then you would take this virtually mediated schema, and then the next step is where you can actually start to apply your analytics, right? So you calculate some probability of fraud again, or apply your model to your probit model to these the virtually mediated schema from real-time transactions or near real-time. That would give you some risk score that then you could in this case, you would compare to the magnitude associated with the risk as well. So now you'd have both the probability and then the amount of the transaction you'd be able to use to represent the magnitude that could be combined to give you a risk rating. So basically how likely something is and how big the problem will be if it actually was fraudulent. Then in turn, you're able to put that on some type of risk score that allows you to deal with these problems differently. So for something that say has a high probability, but a really low amount associated with it, you might go ahead and make the payment anyway, because while you're concerned about it, it won't be problematic enough that it would be worth upsetting the customer if it was legitimate. Whereas on the other hand, there might be something that's a low probability of fraud, but the amount is so high that you need to verify that it's correct before you go ahead and process it. So it allows you to sort of customize the approach that you take by using or leveraging the computer to be able to do this type of analytics really fast. And so these systems, these polyglot systems that feed these types of real-time reporting systems and actually any reporting system now are very, very important, and they're becoming more important within organizations as we found out that it's very easy to apply really high technically savvy analytical models, and in some cases, rather than say like probit model, you could even apply AI functions and like machine learning applications as well. But to do this, the data has to be really good, and it has to be in a way that the model, whether it's an AI-based model or a stochastic model, can actually digest it. And so this process of data integration is really complementary to what's occurring in the innovation in terms of analytics. So it forms this basis of the foundation for analytics to occur. And it's getting more and more important as the models are getting more and more complex and building in more parts to them. So again, thank you for attending. This is a really big topic and there's a lot to it. If you have any questions or anything more you'd like to ask me about it, feel free to contact me. My email address is andrew.harrison@uc.edu, or you can contact anyone from the center and they can get a hold of me too. So thank you very much and have a great day.